All right, we are in deep now. Here come the factorial Anova calculations. This may be one that you might want to watch a couple of times, or at least go over the slides a couple of times. One thing I want to say, these are not any more complicated than the one-factor Anova calculations. It's just that there's more of them. We are going to end up with 3 hypotheses. We're going to end up with 3 F values. They're all constructed exactly the same way we did them with one-factor Anova. So there's not going to be anything qualitatively different. It's just that there's going to be a larger quantity of them. All right, the example I'm going to use here is kind of a classic one from social psychology. If you've taken a social psych course, you may have you may have read this one. It's a pretty interesting study by Cohen and et al. It's called Insult Aggression and the Southern Culture of Honor. The study examined the impacts of an insult on men's testosterone levels. The reason why they focused on testosterone is that testosterone is associated with increases in aggression. As testosterone rises, aggressive tendencies rise. Broadly, they were trying to use this as an experimental explanation for why there's a lot more violence in the South. So we had 2 factors. First, participants were classified as being either from the North or the South, northern states, and this was done at the University of Michigan, so you draw people from all over the country. Northern states, of course, New York, Connecticut, Massachusetts, southern states, Alabama, Mississippi, Oklahoma, Louisiana, places of that nature. Factor B is what the participants experienced. They experienced, and I'll go into this in some more detail, experienced either being bumped or insulted or didn't experience anything unusual. And then the dependent variable was they measured them before this happened and then after this happened. They measured how much their testosterone level changed. So let me just explain the experimental situation. Participants came into the lab. They filled out a questionnaire in one room, where are they from? They took a swab to measure testosterone, and then they walked down a hallway to another room. As they're walking down the hallway, in the hallway, there's somebody who's got a file cabinet open, and the file cabinet is really blocking the whole way. In one condition, the person who's at the file cabinet, just closes it and gets out of the way. The person walks harmlessly by. In the other condition, and you'll see what the different condition names mean here. In the other condition, as the participant's walking down the hall, the person at the filing cabinet slams the filing cabinet closed to let the person by, calls them an asshole, and then kind of bumps into them a little bit. After this, they get to the lab, the other part of the lab. They fill out another questionnaire. They get their testosterone swab, and then after the testosterone readings come back, they measure how much change there was. So the different effects and null hypotheses. First factor is whether you're a northerner or a southerner. You can see the null hypothesis there. We expect them to be equal. Bumped and insulted, we expect those to be equal in our null hypothesis. The interaction, that's asking whether northerners and southerners reacted differently to being bumped and insulted. And the null hypothesis here is always there is no interaction, because there's lots of different ways that can take shape. So in terms of the different formulas, we're going to end up with 3 F values. That's going to require new sums of squares, new mean squares, new degrees of freedom. But as we'll see, it's all really consistent with the one-factor Anova. It stems from that. It's nothing. It's not any more complicated. It's just that there's more of it. So all of these F values are going to have as their denominator mean square within, as before. But in their numerator, you see there's SSA, SSB, and MSA, MSB, and MS interaction. So we're going to have mean squares associated with each of the 3 effects. Otherwise, it's exactly like the one-factor Anova. We're not doing anything different. We're just doing more of the same. The degrees of freedom we deal with, the degrees of freedom within, n minus the number of cells. You can always figure out the number of cells by multiplying the levels of the first factor by the levels of the second factor. We have, in this case, 4, 2 levels and 2 levels. Your factors have to have at least 2 levels. Degrees of freedom A, number of levels of factor A minus 1. Degrees of freedom B, number of levels of factor B minus 1. Degrees of freedom for the interaction, A minus 1 times B minus 1. Or you could say degrees of freedom A times degrees of freedom B. We have 2 levels for all of these, so these are all just going to end up as 1. The different sums of square formulas. Sums of square total is going to be the same as before. Sums of square within is going to be a little bit different in that it's going to be based on the mean of the cell rather than the overall mean. That's the only change there. Sums of square between group, the number of people in the cell times the mean of the cell minus the grand mean squared. Very much the same thing that we did before. We're just swapping out the group for the individual cell. Sums of square A, that's going to be the number of people in each level of A multiplied by the mean for each level of A minus the grand mean squared. So we've got 2 of these, we'll do that twice. Exact same thing for B. And then the interaction just takes the sums of square between and subtracts from it those 2 other sums of squares for A and B. Mean squares are calculated like before. Sums of squares over the corresponding degrees of freedom. So sums of square A over degrees of freedom A, sums of square B over degrees of freedom B, and not surprisingly, sums of square interaction over degrees of freedom interaction. All right, so let's did here. Here what I have are Here what I have all right, here are the data. We need to start off by calculating a number of different mean values. First mean value is the grand mean. That's just the mean of all of the scores in the cell. Then the individual cell means, you can see 2, 4, 3, that's these people here. Whoops. That's the these people right here, the northerners who were not bumped. So we do that for each of the cells. And then we'll need to get overall means for factor A. Factor A was all of the northerners versus all of the southerners. And then the means for factor B, the bumped versus not bumped. And we can see got 3.5 and 8.5 there. So that's the first step, getting all of these mean values. I put the mean values in this table and highlighted them. Sums of square total. I guess I left out the grand mean there. Let me just insert that here so that it's clear. All right. So first up is the sums of square total. Each individual score, so 2, 4, 3, all of those minus 6 squared. Exactly what we did before with one factor Anova and with regression. Sums of square within. Here I'm taking each individual score minus the mean of the cell that it's in. So let's look at the last cell because it's so what I've got there, score of 14 minus the cell mean, which is 12. Score of 10 minus the cell mean of 12. Score of 12 minus the cell mean of 12, each of those squared. So we do that for each individual one, and that gives us the sums of square within. Sums of square between is just the number of people in each cell, and we take the mean of that cell minus the grand mean, the overall mean. So for the first cell, the mean was 3, the grand mean is 6. There's 3 people. We do that. The next one's 3, 4 minus 6, 3 people, 4 minus 6 again. I'm sorry, 5 minus 6, 3 people, 12 minus 6. So that's where we get all of those values, 150. That 150 has got to get parsed out into sums of square A. The number of people in the first level of A, which is 6 people, the 6 northerners who had a mean of 4, minus the overall mean of 6, the 6 Southerners who had a mean of 8, minus the overall mean of 6. Sums of square B, similarly, this is focused on the mean for the not bumped, 3.5. 6 people got not bumped, 6 people got bumped. So we've got our mean of 3.5 minus the grand mean of 6, 8.5 minus the grand mean of 6. And then finally, just some subtraction for the interaction effect, sums of square between minus sums of square A minus sums of square B. For 27, we can see 48 plus 75 plus 27 adds up to that 150 value. All right, that might seem like a lot of work. It's just a lot of detail keeping track of the different pieces on the final homework assignment. You will have a problem like this. It won't be a gigantic amount of data, but I will expect that you know how to do this because I don't believe that hand calculations are useful for work in the real world, but they are very useful for understanding what the different statistics are doing. And that is useful for the real world. All right, degrees of freedom and mean square are going to be pretty straightforward. Oops. Yeah, so degrees of freedom and mean square are pretty straightforward. Degrees of freedom for within and minus the number of cells, we have 12 people, 4 cells for a value of 8. Then we can see the other degrees of freedom, they all fall into 1, 2 levels of A minus 1, 2 levels of B minus 1, and then the interaction just being those two multiplied by each other. The mean square values, mean square within 32 over 8 is 4. All of the other mean square values match the sums of squares because we're just dividing by 1. So again, those parts of the calculations will fly as there's not much to them. Then calculating the F values. So the F values here, it's just the mean square over the corresponding, over mean square within. So for F of A, it's mean square of A over mean square within. For a 12, we get an 18.75 for B and a 6.75 for the interaction. And you can see just reminders of what the null hypotheses are there. To probability values and conclusions, I just put the F value and the corresponding degrees of freedom into the PF command. We see we have a probability that's very low for the first one, so we reject the null hypothesis. There is a main effect that suggests that Southerners were more aggressive than Northerners. Bumped were more aggressive similarly than the not bumped. We see, again, large, it's very small probability value. For the interaction, we again are below that magical 0.05 mark. When we reject here, and we'll come back to interpreting this, at this point we can just, we would just say, okay, there was an interaction. And then we'll get to interpreting that in a little bit. Last calculation we'll talk about is eta squared, or technically this should be written as partial eta squared, because it is actually a slightly different statistic than what we saw before. Partial eta squared is calculated a little bit differently than eta squared. Instead of having sums of square total on the bottom, we have the sums of square for the effect plus the sums of square within. It's called partial because statistically when you take something out, it's called partialing out. We're taking out the influence of sums of square B and sums of square interaction when we're calculating sums of square A. I don't like this statistic. I think it's stupid to partial stuff out because it makes it so you don't get that proportion of variance explained. You get proportion of variance explained out of what could not be explained by the other variables, which isn't a very useful statistic. It's not comparable across different analyses, but it is what people use. So it's what I will show you. We see we do that, we get 0.6, 0.7, and 0.46, again, highlighting how this is not proportion of variance explained because we couldn't explain more than 100% of the variance. But that's how we got that for each of these effects.